It is indeed dangerous to operate electrical systems with an equipment grounding conductor that is not bonded to the neutral at the structure. The core issue arises from the potential for undetected ground faults and the consequential risks of electric shock and fire. The equipment grounding conductor, often abbreviated as EGC, serves as a crucial safety pathway for fault currents. Its primary function is to provide a low-impedance path back to the source, enabling overcurrent protection devices, such as circuit breakers or fuses, to quickly operate and interrupt the flow of electricity in the event of a ground fault. When an equipment grounding conductor is not properly bonded to the neutral at the structure, or if it becomes compromised, several hazardous scenarios can unfold. Firstly, if the equipment grounding conductor is lost or becomes ineffective, a ground fault may not create a sufficient current flow to trip the circuit breaker. This is because the fault current would then have to find an alternative path back to the source, which might involve higher impedance routes through building steel, metallic piping, or even the earth itself. These higher impedance paths limit the magnitude of the fault current, preventing the breaker from tripping. Secondly, the absence of a properly functioning equipment grounding conductor can lead to the accumulation of voltage on metal parts of equipment. This occurs because the fault current, instead of being safely conducted back to the source, may energize any conductive parts that are not effectively grounded. The voltage on these parts can then pose a significant shock hazard to individuals who come into contact with them. Thirdly, the flow of fault current through unintended paths can generate heat, increasing the risk of fire. If the current is forced to flow through combustible materials, such as wood or insulation, the heat generated can ignite these materials, leading to a fire. The equipment grounding conductor plays a vital role in maintaining the integrity of the grounding system as a whole. A properly installed and maintained equipment grounding conductor ensures that the grounding system can effectively dissipate fault currents, protecting both equipment and personnel. The National Electrical Code, or NEC, provides comprehensive guidelines for the installation and maintenance of equipment grounding conductors and grounding systems. It is essential to adhere to these guidelines to ensure electrical safety. Some key considerations for proper equipment grounding include, but are not limited to, firstly, the size of the equipment grounding conductor must be appropriate for the size of the circuit conductors. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the overcurrent protection device rating. Secondly, the equipment grounding conductor must be securely connected to all metal parts of equipment that are likely to become energized. This includes enclosures, raceways, and other conductive components. Thirdly, the equipment grounding conductor must be continuous and unbroken throughout its entire length. Any splices or terminations must be made using approved methods and materials. Fourthly, the equipment grounding conductor must be properly bonded to the neutral at the service entrance or separately derived system. This bonding ensures that the equipment grounding conductor is at the same potential as the neutral, providing a low impedance path for fault currents. Fifthly, regular inspections and testing of the grounding system should be performed to ensure that it is functioning properly. This includes visual inspections of the equipment grounding conductor and testing of the grounding impedance. The consequences of neglecting proper equipment grounding can be severe, ranging from minor electrical shocks to serious injuries or fatalities. It is imperative to prioritize electrical safety and ensure that all electrical systems are installed and maintained in accordance with the NEC and other applicable standards. The equipment grounding conductor is an integral part of the overall grounding system, and its proper functioning is essential for protecting people and property from electrical hazards. In addition to the points mentioned above, it's important to consider the following aspects related to equipment grounding conductors and their role in electrical safety. Let's talk about ground fault circuit interrupters, or GFCIs. While an equipment grounding conductor provides a path for fault current to trip an overcurrent device, a ground fault circuit interrupter, or GFCI, is a different type of protection device that detects even small imbalances in current flow. GFCIs are designed to protect people from electric shock by quickly interrupting the circuit when a ground fault is detected. They are often required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Even with properly installed equipment grounding conductor, GFCIs can provide an additional layer of protection. Next is isolated ground systems. In some sensitive electronic equipment installations, an isolated ground system may be used to minimize electrical noise and interference. In an isolated ground system, the equipment grounding conductor is isolated from the building's main grounding system. This isolation is typically achieved by using an isolated ground receptacle, which is a separate grounding terminal that is not connected to the receptacle's mounting strap. While isolated ground systems can improve the performance of sensitive electronic equipment, they must be installed and maintained carefully to avoid compromising electrical safety. Now let's talk about impedance. The impedance of the equipment grounding conductor is a critical factor in determining its effectiveness. A low impedance equipment grounding conductor provides a better path for fault current, allowing overcurrent devices to trip quickly. Factors that can affect the impedance of the equipment grounding conductor include the size of the conductor, the material of the conductor, and the length of the conductor. The NEC provides guidance on selecting the appropriate size and material for the equipment grounding conductor to ensure that it has a low enough impedance. We should also consider electrical noise. An equipment grounding conductor can also play a role in reducing electrical noise. Electrical noise can interfere with the operation of sensitive electronic equipment, causing malfunctions or data errors. By providing a low impedance path for electrical noise to return to the source, the equipment grounding conductor can help to minimize this interference. However, it's important to note that an equipment grounding conductor is not a substitute for proper shielding and filtering techniques. Now for maintenance and testing. Regular maintenance and testing of the equipment grounding conductor are essential to ensure that it is functioning properly. Visual inspection should be performed to check for any signs of damage or corrosion. Ground impedance testing should be performed to verify that the equipment grounding conductor has a low enough impedance. Any problems that are identified should be corrected promptly. Here are some best practices to remember. Firstly, always consult the NEC and other applicable standards when designing and installing electrical systems. Secondly, use qualified and licensed electricians to perform electrical work. Thirdly, never tamper with or modify electrical equipment. Fourthly, report any electrical hazards to the appropriate authorities. Fifthly, educate yourself and others about electrical safety. Consider surge protection as well. While the equipment grounding conductor is primarily designed to protect against ground faults, it can also provide some degree of protection against voltage surges. Voltage surges can damage sensitive electronic equipment. By providing a lower impedance path for surge current to return to the source, the equipment grounding conductor can help to reduce the severity of voltage surges. However, for optimal surge protection, it is recommended to use dedicated surge protection devices. Now for the purpose of bonding jumpers. Bonding jumpers are used to connect metal parts of equipment together to ensure that they are all at the same potential. Bonding jumpers are often required around knockouts in electrical enclosures. They are also used to bond metal water pipes and gas pipes to the grounding system. Bonding jumpers help to reduce the risk of electric shock by minimizing the voltage difference between different metal parts of equipment. Now on the topic of grounding electrodes. A grounding electrode is a conductive object that is buried in the earth and connected to the grounding system. Grounding electrodes are used to provide a path for fault current to dissipate into the earth. Common types of grounding electrodes include ground rods, ground plates, and underground metal water pipes. The NEC specifies the minimum requirements for grounding electrodes, including the size, material, and installation depth. And let's end on some extra precautions to take. Firstly, always disconnect power before working on electrical equipment. Secondly, use insulated tools and equipment. Thirdly, wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Fourthly, never work on electrical equipment in wet or damp conditions. Fifthly, if you are not qualified to perform electrical work, call a qualified electrician. I'd like to reiterate the importance of adhering to these guidelines, as neglecting proper equipment grounding can have severe consequences, including electrical shock, fire, and equipment damage. It's always better to err on the side of caution when it comes to electrical safety. The equipment grounding conductor is a critical component of any electrical system, and its proper installation and maintenance are essential for protecting people and property from electrical hazards.